Imagine buying a house, right? But when you turn the key and walk in, there are no floors. There are no walls. No electricity.
Just a dirt lot, basically.
Exactly. Just a pile of raw lumber, maybe some bags of concrete, a toolbox, and like a really dense instruction manual.
And no one to call for help.
Right. And in the computing world, millions of highly skilled people actually choose this exact experience every single day, on purpose.
Yeah, they actively seek it out.
They do. So welcome to another custom-tailored deep dive designed specifically for you. Today, we are analyzing a really comprehensive document titled GNU Linux Distributions Overview, Part 4 of 15, Arch Linux. This was produced by the DGU Services Group.
And, looking at the visual materials they provided with the source text, it's actually fascinating to note how this whole overarching series was put together.
Oh yeah, the production tools.
Yeah, they use this whole suite of open source tools. Systems like pop.os, GNU Linux, GIMP for image manipulation, Shotcut for the video editing, and Notebook LM.
All very approachable, pre-configured tools.
Very user-friendly, but we are pushing all of those aside today.
We absolutely are. Our mission today is entirely focused on this enigmatic, highly revered system known as Arch Linux.
And that pile of raw lumber analogy you used, it's incredibly apt, because Arch isn't just handing you unpainted walls, it's handing you the structural framework and basically expecting you to understand load-bearing physics before you even pick up a hammer.
Which is terrifying for most people.
Oh, absolutely. If we look at the glossary provided in our source material, Arch Linux is formally defined as a minimalist, rolling-release GNU Linux distribution.
Right, which sounds like technical jargon, but what does that actually mean for the person sitting at the keyboard?
In practice, it means it violently rejects the modern paradigm of computing. I mean, think about most operating systems today. They hide all their complexity behind these automated graphical installers.
Yeah, the pre-configured desktop environments. Everything is just sort of done for you.
Right. They assume the user wants an appliance. Like a toaster. You just push a button and it works. Arch, on the other hand, assumes the user is an architect.
It provides a blank command line canvas.
Exactly. Just a flashing text cursor in the dark. It expects you to build your operating system block by block, installing only what you explicitly need.
Which fundamentally alters the relationship between the human and the machine, I think. I mean, if a commercial operating system like Windows or Mac OS is a pre-furnished apartment where, moving a wall voids your warranty.
It breaks the plumbing entirely, yeah.
Right. Arch gives you the raw acreage. But this obviously implies a massive barrier to entry. We are talking about a system unapologetically designed for power users.
Unapologetically is the perfect word for it. It isn't trying to capture the everyday consumer market. Not at all. It is built specifically for people who desire a foundational root-level knowledge of their system architecture.
Granular control.
Yes, granular control over every single process running on the CPU. Because when an operating system is pre-configured, compromises are made, right? On behalf of the user.
Yeah, the maintainers decide which display server you need.
Which audio framework handles your sound, what background telemetry services are running, all of it. Arch hands that entire authority back to the user. But to understand why this philosophy even exists, we have to look back to the origins of the project.
Right, because this level of intentional friction, it didn't just emerge in a vacuum.
No, not at all.
So if we trace it back to March 2002, our source notes that a developer named Judd Vinet released the very first iteration of Arch. And it says Vinet was heavily inspired by another minimalist GNU Linux distribution called CRUX.
Yeah, CRUX. He loved the bare bones nature of it, the idea of a system that didn't presume to know what the user wanted.
But CRUX had a glaring mechanical flaw, didn't it, when it came to package management?
It did. The dependency tracking in minimalist distributions back in that era was just notoriously brutal.
Like manual dependency track.
Yes. So imagine you want to compile a piece of software, right? You have to manually fetch the source code. Then you realize, oh wait, this requires 3 specific C libraries. So you go fetch those libraries.
Okay, sounds tedious, but doable.
But then you realize those 3 libraries require older versions of a graphics library, and on and on.
Oh, wow. So it's a recursive nightmare.
A total recursive nightmare of manual configuration. Vinet recognized that, having simplicity in the system architecture shouldn't require you to be agonizingly inefficient when deploying software.
Right. Your time as a developer is valuable.
Exactly. So his solution was to write his own package manager from scratch. He wrote it in the C programming language, and he called it Pacman.
And building pacman in C, that's a crucial detail here, isn't it?
Oh, massively crucial.
Because C is a low-level language. It interacts very intimately with system memory.
Right, which means Pacman was incredibly fast. It managed pre-compiled binary packages with this level of efficiency that completely bypassed the traditional sluggishness of massive relational databases.
The ones used by other package managers at the time.
Exactly. So you have this combination of bare bones, build-it-yourself foundation paired with a lightning-fast C-based package manager, and that immediately attracted a very dedicated following of Linux enthusiasts.
Which brings us to the core philosophy driving Arch, the KISS principle.
Keep it simple, stupid.
Right. But we need to clarify what simple actually means in this context because, the tech industry has heavily distorted that word over the years.
You really have. When a Silicon Valley startup says their new app is simple, what do they mean?
They mean it has one large shiny button.
Exactly, one big button, and all the actual complex algorithmic work is hidden away in a black box on a server somewhere. That is user interface simplicity masking profound structural complexity.
Okay, so how does Arch define simplicity then?
Arch defines it from the perspective of the developer and the system architecture.
I see. So a system with layers of graphical interfaces, automated background daemon scripts, and heavily modified bloatware that is not simple.
No, it's an incredibly complex house of cards, even if it's super easy for the end user to just click a mouse. Arch achieves its version of simplicity by providing raw binaries and basic tools, and specifically by avoiding downstream patches.
Okay, let's break that down because the distinction between upstream and downstream is vital in the source text.
It is. So, when a developer writes a piece of software, let's say a video player, they are the upstream source.
They wrote the original code.
Right. Now, in mainstream distributions, the maintainers of the operating system act as a downstream filter. They take that video player from the upstream developer and they often modify its code.
Why would they modify it?
They might patch it to look better with their default desktop theme, or hard code it to use a specific file path that's unique to their distribution.
Oh, I see. They tailor it.
Exactly. But Arch flatly refuses to do this. Arch utilizes vanilla upstream software.
Vanilla meaning untouched.
Untouched. They package the application exactly as the original developers intended, with zero distribution-specific modifications.
Okay, but if we're avoiding downstream patches, that means we are taking raw upstream code directly from the creators. Doesn't that inherently introduce volatility?
How do you mean?
Well, the whole point of downstream patching in enterprise distributions is to ensure that a piece of software plays nicely with the rest of the highly curated system, right? By throwing raw, unmodified software onto the machine, you are relying entirely on the user to ensure the pieces fit together.
You are. And that is precisely the draw for this specific demographic.
Really?
Yeah, because when a downstream distribution heavily patches software, they introduce opaque custom variables. If that video player crashes on a mainstream distro, you don't know if the bug is in the original developer's code or in the 50 lines of custom patches the distribution maintainers added.
That makes sense. You have no idea whose fault it is.
Right. In Arch, because the software is vanilla, the system remains highly predictable. There are no hidden custom scripts running in the background.
Yeah.
If something breaks, the stack trace points directly to the upstream source.
So it's entirely free of unnecessary bloat, which makes the diagnostic process radically more transparent for the administrator.
It's the difference between debugging a cleanly wired circuit board and trying to figure out why a ball of tangled extension cords isn't carrying a current.
That's a great way to picture it. But this brings us to the release model. That because this philosophy, delivering raw vanilla software directly to the user, it only works if the delivery mechanism is continuous. The source text puts a massive amount of emphasis on the rolling release model.
It does, because the rolling release model defines the day-to-day administration of an Arch system. Most operating systems out there utilize a static point release model.
Like version 1.0, version 2.0.
Exactly. You install version 1.0, and the core libraries are basically frozen in time. You get security patches to fix vulnerabilities, sure, but you don't get new features.
And then what? You wait for the next big release.
Yeah, maybe 2 years later, the maintainers release version 2.0. And that requires this massive, complex upgrade process that often breaks custom configurations because, Thousands of packages are all being updated simultaneously.
Right. Arch completely rejects this artificial freezing of time.
Because software development doesn't actually happen in massive 2-year chunks, it happens continuously.
Yeah.
A developer finishes a feature on a Tuesday, they commit it to their repository, and it's done.
It's ready to be used.
Precisely. So Arch operates on a strict rolling release model. There are no massive version upgrades. As the upstream developers release new code for their software, the Arch maintainers package those binaries and push them straight to the repositories.
Often within hours. The text notes.
Very quickly. So your system updates continuously in these little micro increments. You are always on the absolute bleeding edge of software development. You technically install Arch Linux exactly once.
And from that day forward, the system simply evolves beneath your fingertips with every update command.
Exactly. Which means Arch is uniquely positioned to adopt monumental shifts in Linux architecture long before the enterprise distributions feel comfortable touching them.
Right, like the adoption of systemed, which the text highlights. Arch was a very early and eager adopter of that.
Oh, systemed is a perfect case study of Arch's philosophy in action. For those who might be unfamiliar with the architecture, an initialization system, a init system, is the very first process that the Linux kernel starts during the boot sequence.
Begets process ID 1.
Yes, PID1. It is fundamentally responsible for bringing the rest of the operating system to life, mounting file systems, launching background services like your network managers, logging daemons, everything.
And historically, Linux used very disjointed sequential shell scripts for this, right?
Yeah, it was very slow and messy. Systemed was introduced as this modern, unified software suite to handle all of this concurrently.
But it was incredibly controversial, wasn't it?
Oh, it was a massive ideological battle.
Because the broader Linux community sort of fractured over it. It fundamentally challenged that old UNAX philosophy of having small, isolated programs that do exactly one thing.
Yeah.
Systemti was seen as this monolithic beast that wanted to control everything from logging to network configuration.
Right. And many of the static distributions, the
Yeah.
point release ones, they delayed adopting it for years, partially because of the controversy, but mostly because of the sheer engineering effort required to migrate.
But Arch didn't wait.
No, because of its rolling release nature and its commitment to vanilla upstream development, Arch integrated systems very early. The Arch developers recognized that, beneath all the forum arguments, Systemed actually offered structural elegance.
It offered concurrent service booting, which drastically reduced boot times.
And a highly standardized way of writing service files. They didn't wait for the enterprise world to validate it. They just aligned themselves with the vanguard of upstream Linux development.
And that forward-thinking, flexible architecture has serious modern relevance today. I mean, this isn't just an obscure hobbyist project restricted to server rooms anymore.
Not at all.
Its power is so highly regarded that major commercial hardware is actively relying on it. Our sources point out that SteamOS 3, the operating system powering the Valve Steam Deck, which completely revolutionized the handheld gaming market, was built directly on top of an Arch Linux base.
Valve's decision to base SteamOS 3 on Arch is just a profound validation of the rolling release model. Think about the gaming industry. Hardware drivers, especially graphics drivers, they are updated constantly.
To support new rendering techniques or optimize performance for a game that just launched today.
Exactly. If Valve had built the Steam Deck on a static distribution, like Debian, gamers would be stuck waiting months or even years for upstream graphics driver updates to slowly filter through the testing branches.
By using Arch, Valve can pull the absolute latest graphics libraries from upstream the moment they are available.
Ensuring the hardware runs at peak optimization? Yes.
But, and this is a big but, Valve heavily curates that experience for the Steam Deck user. They hide the complexity behind a beautiful console-like gaming interface. If you, the listener, want to harness that raw power on your own machine, you don't get the curated interface.
You do not.
You have to pass the initiation, right? Achieving that level of lean, tailored performance requires walking through the fire of the manual installation process.
The installation of Arch Linux is, well, it's an educational methodology disguised as a deployment process.
That is a brilliant way to put it.
The source text walks us through this, and it is a stark departure from anything a standard computer user has ever experienced.
Right, so let's walk the listener through it. When you boot the Arch installation media from a USB drive, you aren't greeted by a welcoming GUI asking for your language and time zone.
No welcoming setup wizard. You are dropped into a root shell prompt. A black screen with white text.
You are immediately isolated in a live environment. And because there are no graphical tools holding your hand, the first thing you have to do is manually configure your network connection just to get the machine talking to the outside world.
Because if you don't configure the
You
network,
download anything, you're dead in the water.
exactly. So if you're on Wi-Fi, you're using command line utilities to scan for SSIDs and authenticate. You then manually sync the system clock using the network time protocol.
Why is the clock so important right at the beginning?
Because of cryptography.
Mhm.
You need to ensure that when you eventually download packages, the cryptographic signatures match the current timestamp. If your clock is off, the downloads fail for security reasons.
Oh, wow. Okay, so that's just the preliminary housekeeping. The first true architectural challenge is manual disk partitioning.
Yeah, the installation guide requires you to use command line tools like fdisk or parted to physically map out the storage geometry of your hard drive.
This is where the concept of simple really shows its teeth, I think. Because an automated installer looks at an empty drive and silently decides, okay, I'll put the bootloader here, give the root directory this much space, and allocate this much swap space.
Arch forces you to understand block storage yourself. You have to look at the raw sectors of the NVMe drive or the SSD. You define the exact cylinder boundaries for the EFI system partition. You define the swap partition for memory overflow. You carve out the primary root file system.
You're doing the math.
You are doing the math. And once those partitions are carved out, they're basically just empty mathematical boundaries. You then have to manually format them with the appropriate file systems.
So executing commands to lay down a FAT32 file system for the boot sector, and maybe an XT4 or BTRS file system for the root partition.
Right. And it demands absolute focus because typing the wrong block device identifier, say typing devzsb instead of devsd,
Oh, man.
can instantaneously overwrite a secondary drive containing all your personal data.
The stakes are incredibly real.
Okay.
So you have the storage geometry defined and formatted, but unlike a traditional installation that, extracts a massive pre-configured 3 GB image file onto that newly formatted drive, Arch uses a bootstrapping script
Called Packstrap.
Packstrap.
Packstrap is fascinating because it leverages the pacman package manager from the very first second of the installation.
Okay, how does that work?
Well, instead of unzipping a frozen image, you mount your newly formatted partitions into a temporary directory on the live USB. Then you execute packstrap and point it at that directory. You instruct it to reach out to the global Arch mirror servers and download only the absolute bare minimum packages required for a functional system.
The text mentions downloading the base package, the Linux kernel itself, and the necessary hardware firmware.
The kernel is the critical piece here, right?
Yes, the kernel is the heart of the operation. It's the core engine that acts as the bridge, translating software requests into electrical signals that the physical CPU and RAM can actually execute. So Packstrap downloads the kernel, the GNU core utilities, and the system initialization files, and just drops them into your empty partitions.
It drops them in, yes. But at this point, those files are just sitting there passively. Your computer is still running off the USB drive's kernel.
Right, the live environment.
To actually configure this new skeleton of an operating system you just downloaded, you have to transition into it without rebooting.
And this is accomplished using a command called arch-chroot. The glossary defines chroot as an operation that changes the apparent root directory for the current running process and its children. It's a mechanism that conceptually isolates a process.
It is. To visualize this, imagine putting a set of perfectly convincing VR goggles on your terminal session.
VR goggles. Okay, I like this analogy.
Yeah, so physically, your terminal is still running in the RAM of the live USB environment, but when you execute arch-chroot, the kernel tricks that specific terminal session into perceiving your newly populated hard drive partition as the absolute top-level directory of the universe.
So it restricts the process's vision. You can't see the USB drive anymore. It only sees the incomplete Arch installation.
Exactly. You are stepping inside the simulation of your new operating system while it's still under construction.
You are wiring up the nervous system from the inside.
And the checklist of manual configurations you have to perform while wearing these Chroot VR goggles is exhausting, but it's where the real education happens.
Let's break down the mechanics of those configurations because they illustrate how Linux actually operates under the hood. For instance, the text mentions generating the file system table, the stab.
The stab is crucial. When a computer boots up, the kernel has no idea where your files are. It just sees raw block devices spinning.
Okay.
The famstab is a plain text file that maps the cryptographic UUIDs, the universally unique identifiers of your specific partitions, to the virtual file system tree. You are manually writing the map that tells the kernel, take this specific block of spinning metal and mount it at the home directory.
And if you type a single character of that UUID incorrectly in a text editor like Vim or Nano,
The kernel panics on boot because it literally can't find its own root directory.
the responsibility is entirely yours.
Completely. Next, you have to configure the localization. A computer doesn't inherently know what language to speak or how to format dates and currency.
Right.
You have to edit the locale.gen file, uncomment the specific UTF-8 character sets you need, and run a command to generate those locales inside the GNU C library. You have to manually set the time zone by creating a symbolic link between the global zone info directory and your local eclocal time file.
You are manually defining the machine's perception of space and time.
You really are.
You also have to define the host name, which is literally typing the name you want the machine to be called into a plain text file, so it has an identity when communicating over a network.
But giving it a name doesn't mean it can actually communicate. You have to establish the network stack.
And this trips up so many new users, doesn't it?
Oh, constantly. Because when you run pacstrap earlier, it installs the core utilities, but it does not install a background network management daemon by default.
So if you simply rebooted at this stage,
Your network interface card would sit completely dormant. You have no internet. You have to explicitly use pacman inside the chrooot environment to download a network manager, like Network Manager or System Networked.
and then you have to use the system double command to explicitly enable that daemon to start at boot.
Yes. You are manually instructing the initialization system to bring the network online. It forces you to realize that networking isn't a passive property of a computer. It is an active service that must be managed.
And you have to manage the user security model too. You set the master root password, but running as root for daily tasks is a massive security vulnerability.
Obviously.
Okay.
So you use command line tools to create a standard unprivileged user account. But that user needs a way to elevate privileges when they actually need to install software later on.
Which requires installing the sudo utility.
Right. But merely installing sudo isn't enough. You have to manually edit the sudoers file using a specialized syntax checking tool called vsudo to explicitly grant your new unprivileged user the cryptographic authority to execute commands as the root user.
Every single layer of security is an intentional configuration.
Every single one.
The sheer volume of mechanical steps is staggering. And the final, arguably most critical step before you can attempt to reboot is installing a bootloader. The source mentions grub or system boot.
The bootloader is the crucial intermediary. When you power on a motherboard, its UEFI firmware looks for a specific executable file to hand off control to. The Linux kernel cannot easily be booted directly by the motherboard in all scenarios.
So you need a middleman.
You have to install a bootloader, configure it to find the kernel image you installed via pacstrap, pass it the correct kernel parameter.
Which are essentially text arguments telling the kernel how to behave during the boot process.
Exactly. And apply any microcode updates to patch hardware vulnerabilities in your specific Intel or AMD CPU.
Only after mapping the storage, configuring the space and time locales, building the network stack, setting up the cryptographic security model, and installing the bootloader intermediary, do you finally type exit to take off the chrooot VR goggles.
You take off the goggles, you unmount your partitions, you cross your fingers, and you reboot the physical machine.
And if your syntax was flawless, if your understanding of the architecture was accurate, the motherboard hands off to the bootloader passes the parameters to the kernel mounts the stab, system initializes the services, and you are dropped back into a flashing black command prompt.
The machine is alive.
The machine is alive, which raises a fundamental question. Given that automated installer scripts like arch-install now officially exist, which the source text acknowledges, does going through this terrifying manual process still hold any value?
I get asked this all the time.
I mean, if a Python script can execute all those commands in exactly 3 minutes, why on earth would you, the listener, subject yourself to an hour of manual configuration?
Because the manual process is the point. It is the curriculum. If you use an automated script, you end up with a functional Arch system, yes, but you have learned nothing.
You just have a working computer.
Right. And when a kernel update breaks the boot sequence a month later, or when your network interface suddenly drops its IP address, you are completely blind. You don't know how the system was built.
I see.
By executing the manual installation, you build a mental map of the system. You know exactly where the hefstab is because you wrote it. You know exactly how the network daemon interacts with system because you enabled it. The installation isn't a hurdle meant to annoy you. It is a forced orientation into the mechanics of Linux administration.
It's building mastery through necessary friction.
Perfectly said.
But let's say you've done it. You reboot, you log in, and you are staring at a black screen. The system is breathing, but it has no limbs. There is no graphical desktop, no web browser, no sound.
It's just a core.
This is where package management dictates the entire architecture moving forward. We need to dissect Arch's secret weapons for raising the walls of this empty house.
The primary weapon, the absolute core of the system's daily operation, is pacman. We touched on its C-based origins earlier, but we really need to dive into the mathematical mechanics of how it resolves dependencies.
Okay, let's do it.
When you request a piece of software, pacman doesn't just blindly download a file. It analyzes the package, pulls the metadata, and calculates complex dependency graphs.
Because modern software is inherently modular, a video editor isn't one monolithic block of code. It relies on separate libraries for audio encoding, video rendering, drawing the graphical user interface.
Exactly. pacman looks at the software you want, figures out the 20 other libraries that software needs to function, checks its local database to see which of those libraries are already installed on your system to avoid redundancy.
To save time and space.
Right, and then it reaches out to the mirror servers to download the specific pre-compiled tarballs required to satisfy the graph.
It is solving a massive logic puzzle in real time. And what makes pacman so heavily praised in the engineering community is its raw speed. While enterprise distributions use complex, heavy relational databases to track installed packages, pacman uses a minimalist, text-based database.
The text-based database design is just brilliant. It strips away all the overhead of SQL queries. When you execute an installation command, pacman reads the plain text files, resolves the dependency math almost instantaneously in memory, downloads the compressed tar archives,
Which are the actual software packages.
right, extracts the binaries directly into the correct paths in the file system, and writes a new text file to log the installation. The entire operation is atomic and blisteringly fast.
And to update the entire system, pulling in every new bleeding-edge package available globally, you just simply type pacman-cu.
It syncs the master database, upgrades the core system, and you are back to work in seconds.
That handles the official, vetted software in the main repositories. But the reality of computing is that users need obscure tools. What if you need a niche piece of bioinformatics software, or a proprietary printer driver, or a beta version of a tool that hasn't been officially packaged yet? In most distributions, this means hunting down random installation files on the internet and polluting your clean system.
Which is a nightmare to manage.
But Arch solves this elegantly with the AUR.
The Arch User Repository. The AUR is arguably the defining characteristic of the Arch ecosystem. It is a massive, community-driven library. The unwritten rule in the Linux community is, if a piece of open-source software exists anywhere in the world, someone has already written an AUR script for it.
But crucially, the AUR does not contain precompiled binaries. The Arch servers do not host the actual software. The AUR is entirely comprised of PKGBL scripts.
Let's unpack the mechanics of a PKGBL. The glossary defines this as a shell script that contains the necessary variables and instructions to compile and build a software package.
It's essentially a highly standardized recipe.
It is a recipe written in bash shell syntax. When you interact with the AUR, you use a core tool called makekg. Let's say you find a PKGBLD for a rare piece of software. You download that text file to your machine and run the makekg command.
And what does it do?
The tool reads the variables defined in the script. It automatically reaches out across the internet to the original developer's GitHub repository or web server and fetches the raw, uncompiled source code.
But fetching arbitrary source code from the internet sounds like a massive security vulnerability. How does makekg ensure that the code it just downloaded hasn't been intercepted or tampered with by a malicious third party?
Cryptographic verification is baked into the PKGBUL standard. Before makekg even attempts to compile the software, it reads the cryptographic checksums, usually SHA-256 hashes defined by the script author.
So it hashes the downloaded source code locally.
And compares the two strings. If they don't match perfectly, the process halts immediately. Many scripts also utilize GPG keys to verify the digital signature of the upstream developer.
So it fetches the code, verifies the cryptography, and then what? It actually runs the compiler right there on your local CPU.
Yes. It executes the make commands defined in the script, compiling the raw C or Rust or Python code into executable binaries optimized for your architecture. And then comes the brilliant part. Make.pg doesn't just scatter those newly compiled files across your hard drive.
Because that would be exactly like polluting your system with random internet installers.
Exactly. Instead, it gathers the finished binaries and wraps them into a standard pacman-compatible tarball archive.
Oh, that is incredibly elegant. You get the best of both
I
worlds.
really do.
You get the incredible speed of pre-compiled binary packages for your core operating system via pacman, but you also have the total flexibility to build custom, highly obscure software from raw source code, and it's all managed under the exact same package management system.
You can uninstall that obscure source-compiled software with the exact same pacman command you use to uninstall a standard web browser. It brings the inherent chaos of source code compilation under the disciplined, mathematically rigorous management of pacman.
It ensures your file system remains pristine, regardless of how experimental your software choices are.
Yes.
And navigating this complex ecosystem of compilation and configuration is made possible by Arch's ultimate secret weapon, the Arch Wiki.
Oh, the Arch Wiki. It's legendary.
The source text highlights the legendary status of the Arch Wiki. It is not an exaggeration to say that it is renowned throughout the entire open source industry as the ultimate troubleshooting resource.
You could be running a completely different operating system, say Ubuntu or Fedora, run into a highly obscure problem with your Bluetooth configuration.
And the best, most technically accurate answer on the internet will almost always be found on the Arch Wiki.
Because the Arch philosophy demands manual configuration of everything, the community has had no choice but to meticulously document every single piece of Linux software and exactly how it interacts with the underlying kernel and systemed components.
It isn't just a manual. It is a masterwork of collaborative, peer-reviewed engineering documentation. It explains the why behind the configurations.
But, we should talk about the security aspect of the AUR again.
Yeah, let me put my skeptic's hat on for a second because I want to push back on the security model of the AUR. You mentioned it's a massive community-driven library. If you are downloading PKGBS scripts written by complete strangers, aren't you essentially executing arbitrary shell commands with administrative privileges?
You are.
The security model isn't a walled garden vetted by a corporation. It sounds like a glass house. How is that secure?
Your skepticism is entirely warranted, and the Arch community would applaud you for it. The transparency of the system is its primary security mechanism. Yes, executing a script from a stranger carries inherent risk, but a PKGB build is not a compiled, obfuscated binary file hiding its true intentions.
It's just a text file.
It is a plain text shell script, usually less than 50 lines long. The entire Arch philosophy dictates that the administrator, you must open that recipe in a text editor and read it line by line before ever executing make.pg.
You have to audit the code yourself. You look at the source URL to ensure it's actually pointing to the legitimate developer's website and not a malicious clone.
You read the build functions to ensure it isn't trying to silently inject a crypto miner into the compile process or alias your sudo command.
Exactly. It enforces a culture of self-reliance and code literacy. The operating system does not protect you by locking you out and saying, "Trust us, our corporate security team vetted this."
It protects you by handing you the blueprints, turning on the floodlights and saying, you are the system's administrator, read the code, verify the variables yourself.
It trusts your intelligence, but it strictly demands your diligence, which fundamentally shifts the user's relationship with technology. This culture of literacy and self-reliance is exactly why Arch isn't just an operating system. It brings us into the realm of Arch as a masterclass in computer science.
Managing an Arch system long-term is a profound educational journey. As the source text states, it strips away the automated magic.
The automated magic.
Yeah. When you use a mainstream operating system, you double-click a graphical icon and a program simply appears on screen. You are completely shielded from the complex interplay of the display server protocol, the memory allocation mechanisms, and the kernel file system permissions making that happen.
The text specifically mentions mastering modern Linux plumbing. Because the Packstrap installation provides no default graphical user interface, the administrator is the one who has to assemble the desktop environment from scratch.
You don't just get a desktop. You have to research the underlying technologies and make architectural decisions.
And those decisions require deep technical understanding. You have to choose a display server protocol. Are you going to use the legacy Xorg server, which has decades of compatibility but a convoluted security model?
Yeah.
Or are you going to implement Wayland, the modern compositor protocol that isolates client windows for better security, but requires configuring modern graphics drivers.
You have to understand how pixels actually get drawn to the screen. And once you have a display server, you have to choose a window manager to actually draw the borders around your applications and handle keyboard shortcuts.
You have to choose an audio framework. Are you installing Pulse Audio, or are you migrating to the newer Pipewire for better low-latency inter-process communication?
You are acting as the systems integrator. You are wiring the plumbing of the house.
And through that integration process, you master tools that are absolutely critical in professional IT and computer science roles. You become intimately familiar with systems, writing your own custom service files to manage background tasks and ensure they start in the correct dependency order.
You learn about UDEV, the dynamic device manager. You start to understand exactly how the Linux kernel reacts when you plug in a USB drive, how it identifies the hardware, creates a dynamic node in the dev directory, and triggers a script to mount the file system. You understand the network stacks at a fundamental routing table level.
It also changes how you interact with the broader software development world. We talked earlier about upstream versus downstream software because Arch avoids downstream patches. You are using the software exactly as the creator intended.
Which means when a bug happens, and let's be honest, in a bleeding-edge rolling release environment, bugs are going to happen.
Oh, inevitably.
Your diagnostic process is entirely different. You aren't going to a user forum complaining to the distribution maintainers. Our sources point out that users often end up collaborating directly with the upstream developers.
That is a critical transition. Because your system is running vanilla code, your bug reports are highly valuable to the original developers. You are testing their raw code in the wild.
If a new version of a Wayland compositor crashes, you use the journal antil command to pull the highly detailed system logs directly from systemd, identify the exact memory segmentation fault, navigate to the developer's Git repository, and submit a detailed bug report.
You become an active, contributing participant in the free software ecosystem rather than a passive consumer of a packaged product.
Exactly.
It makes me think, if you're a computer science student or a junior sysadmin or just someone who is insanely curious and wants to know how the digital world actually operates, building and maintaining Arch sounds like the ultimate final exam for modern computing.
It really is.
You aren't just learning how to operate the vehicle. You are literally building the engine block from scratch, machining the pistons, and wiring the alternator. The natural result is that you automatically know how to diagnose and fix it when it breaks, because you know the exact torque specs of every bolt.
This is the most valuable takeaway from the Arch experience. It shifts the listener's mindset entirely. You transition from being a software consumer to a systems architect.
That's a powerful shift.
When you spend your time meticulously managing configuration files, reading dense system journals to diagnose driver conflicts, and auditing shell scripts from the AUR, you are building a highly specialized technical vocabulary.
And that vocabulary translates perfectly to the professional world. The skills you learn troubleshooting a broken network bridge in Arch apply directly to managing massive enterprise server clusters, optimizing Docker containers and cloud deployments, and understanding complex distributed computing environments across the board.
It gives you the keys to the kingdom. You are no longer intimidated by the command line. It becomes your primary interface for logical problem solving.
But to truly appreciate the specific utility of this architectural approach, we need to line Arch up against the other heavyweights in the Linux ecosystem.
Right, because Arch's philosophy is extreme, and it isn't operating in a vacuum. There are other incredibly powerful philosophies out there that solve different problems. Let's break down the comparative analysis provided in the source material to highlight Arch's specific niche.
Comparisons are the best way to define a tool's true boundaries. Let's start with a comparison between Arch and Gentoo Linux. Now, Gentoo is another highly respected minimalist distribution that appeals heavily to the do-it-yourself power user crowd. If they are both targeting the DIY systems architect, how do they fundamentally differ in their approach?
They are exact opposites in their software delivery mechanisms. As we've extensively discussed, Arch uses pacman to deliver precompiled binaries. The software is compiled on the Arch build servers, and you download the finished product. It's built for rapid deployment.
Right.
Gentoo, on the other hand, forces the administrator to compile almost everything from raw source code locally on their own machine.
Which takes a massive amount of time and CPU power. I mean, compiling a web browser from source can take hours. Why would anyone want to compile their entire operating system locally?
Hyper-specific hardware optimization. When the Arch servers compile a binary, they have to use generic instruction sets that will work on almost any modern 64-bit CPU.
A one-size-fits-most approach.
Exactly. When you compile software locally on Gentoo, you pass specific compiler flags, like March Native, that instruct the compiler to optimize the code perfectly for the exact specific silicon architecture of the CPU currently sitting in your motherboard. You squeeze out every theoretical drop of performance.
So Arch prioritizes administrative efficiency and quick updates, deliberately sacrificing that hyper-specific local optimization for the sheer speed of binary distribution.
Yes. Arch trades a tiny fraction of a percent of theoretical computational optimization for a massive increase in day-to-day usability and deployment speed.
That makes perfect sense. Okay, next up, the source text compares Arch to Debian. And this is a clash of philosophical titans because Debian is one of the oldest, most foundational, and most widely deployed distributions in existence.
It powers massive swaths of the internet's infrastructure.
Right.
Their philosophies are entirely divergent, representing the two extremes of software deployment. Debian prioritizes unshakable mathematical stability above all else. It utilizes a static point release model.
Which we discussed earlier.
Right. Software in the Debian stable branch is not new. It has been rigorously tested, analyzed, and frozen in time, often for years, to ensure that it will absolutely never crash or produce unexpected behavior. It is the perfect, immovable foundation for enterprise servers where uptime is measured in years and where a crashed service costs millions of dollars.
But the trade-off for that stability is that the software is inherently old. Arch, conversely, completely rejects static testing phases for the bleeding-edge rolling model.
Exactly. Arch is not trying to be a stable server foundation for a Fortune 500 company. It's trying to provide software developers, security researchers, and power users with the absolute newest compilers, libraries, and features the very moment the upstream developers publish them.
Debian is the unbreakable vault. Arch is the cutting-edge laboratory. If you need a server to route traffic for 5 years without rebooting, you use Debian. If you are a developer writing code for a hardware framework that was released yesterday, you use Arch.
The right tool for the exact right job.
Okay, what about Arch versus Slackware? The text notes that both of these distributions highly value the KISS principle, keep it simple, stupid. But they interpret the definition of simplicity in fundamentally different ways when it comes to package management.
This is a fascinating architectural debate. Slackware is the oldest surviving Linux distribution, and its philosophy is uncompromising. Slackware believes that a package manager should be a very simple tool that simply extracts files onto a hard drive, period. It flatly refuses to automate dependency resolution.
Meaning, if you want to install a complex program on Slackware, and that program requires 5 specific external libraries to function, the Slackware package manager won't go get them for you.
No, it won't.
It expects you, the administrator, to manually track down the source code for those 5 libraries, compile them, and install them in the correct order before the main program will even execute.
Exactly. The Slackware philosophy argues that this is true simplicity because the package manager itself is doing the bare minimum. There is no complex dependency resolution logic that can break or make assumptions on your behalf.
Okay, but Arch.
Arch respects the KISS principle, but it applies a pragmatic limit. Arch embraces automated dependency resolution via pacman. The Arch philosophy argues that having a human manually track down dependencies is a waste of intellectual capital. The computer is better at dependency math, so let the package manager be fast, automated, and efficient at resolving the graphs, while leaving the actual configuration of the software to the manual control of the user.
So Slackware makes you do the tedious fetch quests to gather the materials, while Arch automates the logistics of delivering the materials, but still forces you to build the house.
That is a highly pragmatic distinction.
And finally, the text compares Arch to Manjaro Linux. Now, Manjaro is heavily popularized and is actually built on top of the Arch Linux base. They use the same package formats, so why aren't they considered the same thing?
It comes down to execution and the intended target audience. Manjaro takes the powerful Arch base and fundamentally alters the user experience to appeal to the mainstream consumer. Remember the grueling manual command line installation process we detailed earlier?
The Croot VR goggles.
Right. Manjaro replaces that with a standard, user-friendly graphical installer. You click Next a few times, and it handles the partitioning and configuration for you. It provides heavily pre-configured desktop environments with customized themes right out of the box.
Which immediately violates the core Arch philosophy of the user building the system block by block. But doesn't Manjaro also change the software delivery model?
It does, and that is the critical technical divergence. Manjaro maintains its own software repositories. They intercept the bleeding-edge updates from Arch, and they deliberately hold them back for a period of time, usually a few weeks, to conduct their own internal stability testing before pushing them to Manjaro users.
Arch fundamentally rejects this. Arch forces the user to utilize entirely vanilla upstream code with absolute zero delay on updates. Manjaro introduces a downstream layer of testing and configuration. Arch demands raw immediacy. Okay, looking at this lineup, I have to ask a major overarching question. You just mentioned that Debian offers unshakable stability. And looking back at the source text, it explicitly admits that the primary barrier to using Arch is its propensity for occasional system breakages.
That is the reality of the architecture. Delivering the newest software immediately, without a downstream testing phase, means bugs inevitably slip through.
So if you are the listener weighing your options for your primary workstation, why on earth would you choose an operating system that might randomly break after a routine update over one that is rock solid and guaranteed to work?
That is the defining question of systems administration, and it comes down to a critical evaluation of risk versus reward. Yes, running Arch requires accepting a baseline level of maintenance risk. You might execute pacman say update your system, reboot, and suddenly find that your graphical display server refuses to start because a new upstream driver has a bug that conflicts with your specific graphics card.
Which sounds like a nightmare if you're on a deadline.
It can be. You are forced to drop into a command line interface, read the system journals, consult the Arch wiki, manually downgrade the offending package, and repair the system.
But the reward for accepting that risk?
The reward for accepting that risk and for building the technical competence to quickly resolve those issues is immediate access to the future of computing.
Access to the future. That is a compelling way to phrase it.
It is the practical reality. If you are a machine learning researcher utilizing the absolute newest Python libraries and CUD rendering cores, or a software developer writing code for hardware architectures that were finalized last month, or even a competitive gamer needing the latest Mesa graphics drivers to support a rendering pipeline for a game that launched today, waiting 2 years for a stable Debian release to validate those tools is completely unacceptable.
Your work demands the bleeding edge.
Having tomorrow's computational tools today, having access to new architectural features and massive performance upgrades long before standard distributions even begin testing them, is absolutely worth the occasional 15 minutes of troubleshooting.
It's a calculated trade-off. You trade the peace of mind of a static system for the raw velocity of the bleeding edge. And because you built the system manually from the ground up, you already possess the architectural knowledge to fix it when the bleeding edge occasionally cuts you. It ultimately leaves the user with a machine that is perfectly dynamically tailored to their exact computational needs. Which brings us to the conclusion of our deep dive today. Let's synthesize the core takeaway from this extensive exploration of the Djere Services Group document. Arch Linux represents the ultimate DIY binary experience. It is a technological framework where the systems administrator is the ultimate unquestioned authority.
There are no default web browsers making assumptions about your privacy. There are no default media players, no background telemetry demons, and absolutely no bloatware.
Every single application, every running service, every line of configuration mapping a partition on that hard drive is there because the administrator explicitly manually engineered it to be there. The result is a radically lean, lightning-fast, low-resource machine that executes commands with zero overhead.
And that profound level of administrative control connects directly back to the value it provides you, the listener. The computing landscape is increasingly complex. Whether you are prepping for a high-level IT infrastructure role and need to master the command line and systemed interactions,
or whether you are a developer who desperately needs bleeding-edge libraries for your compilation pipelines.
Or whether you are simply a technology enthusiast who desires complete, unmitigated authority over the hardware you purchased. Arch provides the definitive educational foundation. The architectural skills you forge while building and maintaining an Arch system are permanent, and they translate to every tier of the tech industry.
It is an intense methodology, but it is undeniably powerful. And this deep dive is just one component of a much larger analytical series. Having explored the extreme edges of manual DIY configuration and bleeding-edge rolling releases today, the source material teases that the next installment will pivot to the exact opposite philosophy.
Next time, we will be looking at Debian GNU Linux. exploring how a massive, highly organized community approached the monumental challenge of universal software delivery to build one of the most reliable, rock-solid, automated binary systems in human history.
It will be a fascinating contrast, exploring the engineering required to create an immovable rock after spending today dissecting the cutting edge.
Absolutely. The contrast is what makes the ecosystem so robust.
But before we wrap this up, and before you go back to your day, I want to leave you with a lingering philosophical question to mull over. Something that builds on the architectural concepts we've dissected today, but challenges how we interact with technology on a daily basis. Think about this. In a world where our smart devices, our phones, and our commercial computers are increasingly locked down.
Hiding their inner workings behind sleek, unchangeable, automated interfaces that we aren't legally or practically allowed to touch.
Right. What does it really mean to reclaim absolute control? If you don't know exactly what every line of code, every background service, and every network daemon on your machine is doing, if you are just blindly trusting the manufacturer's automated setup, who really owns your computer? You or the manufacturer?